Welcome all to this lecture series on ESP32. I am Priya, working at Intelligent Devices and Smart Solutions. This is second lecture, ESP Introduction of Module 1, Introduction and System Setup of ESP32 Room 32E. In this lecture, we will see features of the selected ESP32 module, that is ESP32 Room 32E. We will see the hardware requirements and software requirements of this course. ESP32 Room 32 is based on the Xtensa 32-bit LX6 microprocessor. It has 448 kilobytes ROM and 520 kilobytes of SRAM. It has 16 kilobytes SRAM in RTC. It supports QSPI. QSPI is Quad SPI. It is enhanced version of SPI that allows data to be transferred 4 bits at a time instead of 1, thus providing a much higher throughput. It is very useful for external memory interface with multiple Flash and SRAM chips. ESP32 also supports Wi-Fi standards. It supports IEEE 802.11 BGN. IEEE 802.11 refers to the family of Wi-Fi standards, and B, G and N are the different versions. Version B was introduced in 1999 and it had a speed of 11 megabits per second. G was introduced in 2003 and it had a speed of 54 megabits per second. N came in 2009 and it had a speed of 600 megabits per second. In 2009, 5 GHz band was also introduced in the 802.11 standard and it was called Wi-Fi 4. Further, AC which was also called Wi-Fi 5 and EX which was called Wi-Fi 6 and Wi-Fi 6E were also introduced, which are the latest standards. ESP32 is based on 2.4 GHz band. It has a speed of up to 150 megabits per second. It works with most of the home and IoT networks. ESP32 works in multiple Wi-Fi modes: station mode, soft AP mode, promisor mode, and it can run in all the modes simultaneously. In station mode, it connects to an existing Wi-Fi network. In soft AP mode, it creates its own access point and other devices can connect to it. It creates its Wi-Fi hotspot and other Wi-Fi devices can connect to it. In promisor mode, it listens to nearby Wi-Fi packets. It also supports Wi-Fi multimedia. In this, it prioritizes voice, video and data traffic. It reduces lag and improves streaming quality. ESP32 also supports Bluetooth. It supports dual mode Bluetooth V4.2. V4.2 is the Bluetooth version 4.2 that was introduced by SIG, Bluetooth SIG, Special Interest Group, in 2014. In dual mode, it supports Bluetooth Classic, BR, EDR. BR means basic rate and enhanced data rate, and also it supports Bluetooth Low Energy. For classic Bluetooth, it is used for high-speed data transfer, which is used during the transfer of files or during audio or video transfer. And low energy is for the IoT applications, Bluetooth Low Energy. Transmission power up to plus 9 dBm output. It provides a strong wireless range without needing an external amplifier. Receiver sensitivity is 94 dBm for BLE. Next, it has excellent signal reception even at longer distances. Adaptive frequency hopping. Adaptive frequency hopping is a technique Adaptive frequency hopping it automatically avoids crowded channels. It reduces interference with Wi-Fi and other Bluetooth devices. It is a technique used by Bluetooth to reduce interference and improve connection reliability in 2.4 GHz. As we know, both Bluetooth and Wi-Fi devices work in 2.4 GHz band. It stretches from 2400 MHz to 2483.5 MHz, and it is divided into 79 channels, each channel being 1 MHz wide. Bluetooth hops from one channel to another 1600 times per second. This is called frequency hopping. The Bluetooth device monitors channel quality. It marks channel bad if there is too much interference with other Bluetooth devices or Wi-Fi devices. And in the future hoppings, the device will skip these channels. ESP32 has lot of peripherals attached to it. It has 34 programmable GPIOs for digital input-output. It has dedicated input-only pins and reserved pins for Flash and PSRAM. It has ADC peripheral attached to it. ADC is a hardware. It converts analog voltage to digital numbers that MCU can process. It has 12-bit SCR ADC supporting up to 18 channels. This SCR is successive approximation register. It is a ADC architecture. ESP32 as well as STM32 uses this architecture. Try big is the resolution of this ADC. Playback means it can divide the reference voltage. Suppose our reference voltage is 3.3 volt. Then 12-bit resolution means 2 to the power 12 levels. It can divide this voltage from 0 to 3.3. Thus, each voltage step is 3.3 volt divided by 2 to the power 12. That is 3.3 volt divided by 4096. And it comes up to be 0.8 millivolt. It converts analog signals, sensors, potentiometers into digital values. DAC is digital to analog converter. It has two 8-bit DACs that converts digital signals to analog voltage for audio or control. It has touch sensors. It has 10 capacitive touch sensors. The ESP32 touch sensors work on the principle of capacitive sensing. Every conducting object like our fingers or the pad attached to the pins, these pins have copper or aluminum foils attached. So they have some capacitance. When we touch these pads, the capacitance changes, and this change in capacitance is sensed by the ESP32. How it does is ESP32 charges the pad slightly. It then measures how long it takes for the charge to leak away or for the voltage to drop below a threshold. The time taken by this in this leak away corresponds to the capacitance. So when we touch this pad, the capacitance increases. Then it also supports SPI interface. It has 4 SPI interfaces. It is used for high speed communication and displays sensors or external flash. SPI uses 4 pins, 4 wires for communication. It is MOSI, MISO, clock and chip select. The MCU can be connected to a number of SPI sensors or SPI devices. So, the MOSI, MISO and clock pin will be common to all the sensors. The chip select one GPIO pin from MCU will connect to the chip select pin of the sensor of each of the sensors. And these pins will be used by the MCU to select to which sensor it wants to communicate to. It also supports I2S interface. It is for sound communication. It handles digital audio input output for microphones or speakers. It is a serial bus standard to transfer audio between ICs. There are two I2S interfaces. We will see all these peripherals in detail when we work with ESP32 and sensors. It has two I2C interfaces. It connects multiple low speed peripherals like sensors or RTC modules. It has three UART interfaces. It enables serial communication with PCs, modules or other MCUs. We use FTDI cable to communicate our PC with MCU. We will connect the TX pin of the FTDI to the RX pin of the MCU and RX pin of the FTDI to TX pin of the MCU, and we will connect the FTDI cable to the PC. The transmission from the MCU, we will get this via UART and we can see this in the terminal or in any of the serial monitor. It enables serial communication with PCs, modules and other hosts. It also supports SD host interface. It has one host interface and one slave SDIO SPI. It supports SDI is SD card storage or peripheral communication. So the SD host interface, it is a hardware block inside the MCU that can communicate with SD memory card or SDIO device. SDIO is Secure Data Input Output Protocol. So any device that supports this protocol can communicate via SD interface. So this ESP32 can act as host or master controller, and it can connect to the SD card or other SBIO devices. In this case, the ESP32 acts as the master or controller. It can also act as a slave and connect it to a master or other MCU that supports SDI. It supports SD card storage or peripheral communication. Pulse counter. The ESP32 supports pulse counter. It counts external pulses from the sensors or rotary encoders. It is useful for speed, rotation or flow measurements. Ethernet MAC. ESP32 also supports Ethernet communication. ESP32 has Ethernet MAC. MAC stands for Media Access Controller. So it's the digital half of the Ethernet communication. Ethernet communication has two parts. Digital half, that is the NAC, and the PHY is the analog part. So it handles Ethernet frame, digital signal, address, CRC, buffering, BME, etc. The PHY part is not there in the ESP32, but we can attach a peripheral PHY chip like LAN 8720 or chip like BP 83848 etc. to the ESP32. Then MAC will communicate with LAN 8720 chip via RMII, and this PHY layer PHY will connect to the RJ45 connector, which will communicate with the cable. This is the analog part. So we'll see this in details. So it thus ESP32 supports Ethernet communication. CAN bus or TWI. It is two-wire interface. CAN bus, it is a serial communication protocol. It was designed by Bosch for automotive industry, but it can also be used for robotics and other industrial setup. It is a messages based broadcasting. It is not address based. It will broadcast message ID and data, and each node will see every message, and the nodes may ignore or process depending on this situation. RMP, remote control. It can precisely generate or measure digital waveforms, especially timing based signals. It is a TX-RX controller for precise timing signals. It is useful for IR remote control, LED driving or pulse modulation. ESP32 also has motor PWM. ESP32 can generate PWM signal to control motor's speed and direction. It is useful for robotics, servo motors and DC motor control. It has LED PWM. It supports up to 16 PWM channels. It can dim LEDs or control brightness independently for multiple LEDs. ESP32 supports 5-hour modes. It is active, that is the normal running mode, modern sleep, light sleep, deep sleep, hibernation. Deep sleep is the lowest power consuming mode and it consumes 10 microamps. During the deep sleep, there is a small power, ultra low power coprocessor that is staying awake, and it has RTC IO pins that it can connect to sensors and keep collecting data while the main processor is in sleep mode. It can execute simple tasks while main CPU is sleeping. It is ideal for sensors and data logging without waking full processors. So there is RTC memory space where it retains data during the deep sleep. This ULP also accesses this RTC memory, and while the main microcontroller is sleeping, main processor is sleeping, this ULP will use this RTC memory and store data on it. And when the processor wakes up, or the ULP can wake it up, when this processor wakes up, it will use this data and process it. ESP32 security features. It has secure boot and flash encryption. It prevents unauthorized firmware from running. It keeps stored data safe from tampering. It has one-time programmable OTP memory. Out of 1024 bit, up to 768 bits are for user application. It stores keys and security critical data securely. Cryptographic hardware acceleration. It supports AES, SHA-2, RSA, ECC and random number generation. This hardware acceleration speeds up encryption and authentication operation for secure communication. Node configuration. There are two stepping pins. There are many stepping pins, but two of them controls the boot modes. The stepping pins are the pins whose states are checked at the reset, and corresponding decisions and appropriate decisions are taken at the MCU level. Starting pins GPIO 0 and GPIO 2 control the boot modes. When GPIO 0 is low, it enters UART download mode. It is used for flashing the firmware. When it is high, it boots from the internal flash. GPIO 2 typically is high during boot for normal operation. It influences SPI flash boot behavior. Boot mode selection is hardware controlled at reset, so correct pull-ups, pull-downs on these pins are crucial for reliable flashing and normal startup. Hardware and software requirements. ESP32 development board will be needed. Micro USB cable, USB type A to micro USB. This cable will be used to power up the ESP32 and for serial communication between PC and ESP32 module. Then we will need breadboards and jumper wire for prototyping circuits and connecting sensors. We will need a list of sensors. Some I have listed here, but the list will be large and we'll try to connect as many sensors as possible. Power supply, it is optional, but for some of the sensors it will be a must because ESP32 has only 3.3 volt output. So for sensors that require 5 volt power supply, we will have to supply it externally from a power source. Then we will need serial to USB drivers like FTDI cable or some other serial TTN converter. WISP IDF. Then software requirements. We will be using Ubuntu 22.04. We will use VS Code with ESP IDF extension installed in it. We will use 5.5 version, which is the latest stable version release. We will need serial monitor tool like screen or putty or teraterm to display serial output, debug messages and other serial messages. We will be using screen. Thank you. We see you in the next lecture.